Hello, and welcome to Backer Breaks It Down. In this episode, we are going to focus on objective number 2 here, sketching the graph of a piecewise defined function and describing its domain and range. We'll then also write a piecewise function given its graph. So we're focusing on the graphs of piecewise defined functions here. Okay, so the piecewise functions that you are going to graph are going to be made up of linear pieces. So I just wanted to review with you graphing lines. First off, the easy one, graphing of a horizontal line. So whenever we see a number in our piecewise function, we're going to graph a horizontal line. It's going to go through that number on the y-axis. Okay. All of our other lines, we're going to be given them in slope-intercept form. Slope-intercept form is y equals mx plus b. You definitely want to start by plotting the vertical intercept. Now, no matter what, we are going to be starting on the y-axis. That's where your y-intercept goes, okay? So that's where your starting point will always be located. From there, we're just going to do what the slope tells us to do, okay? So the first thing we do is we address the number in the numerator of our slope, and then we will address what's happening in the denominator. If the slope is positive, you're going to go up the number of units in that numerator. And if it's negative, you're going to go down the number of units in the numerator. Okay. Always go right the number of units in the denominator. So for example, in the graph below, it says graph y equals negative 3/5 x plus 4. So you're starting on the y-axis at 4. And since the slope is negative 3/5, since it's negative, we're going to go down the 3 units in the numerator, and then we're always going to go right the number in the denominator. So from that starting point, they went down 3 and right 5. That gave us a second point, and that's our line. Just use your straight edge and make a line, okay? So our piecewise functions will be made up of linear pieces, okay? And as you know, each of these linear pieces is going to, well, only exist in part of our coordinate plane and not the entire coordinate plane. So here's like an example of how we go about graphing piecewise functions. So each piece of our piecewise function has its own neighborhood that they're going to like reside in. So the first thing we have to do is we have to put up some fences, okay? And that's what they are talking about here, right? And so this particular piecewise function has one fence, and it's at x is 1. And so as you can see, they drew this dashed line at x is equal to 1, and that's the fence, okay? So the first piece, x plus 2, lives in the neighborhood where the x values are less than 1. All right, so that is the neighborhood on the left. They're even indicating that y equals x plus 2 lives here in the neighborhood on the left. And so then we need to graph that piece. So it is a line. So what that means is we are going to start at 2 on the y-axis, because we always start on the y-axis. And since the slope is 1, we're going to go up 1, right 1, okay? So they're not showing the entire line here. But honestly, whenever I'm graphing piecewise functions, I will graph my entire line, okay? And then I will erase the part that's in the wrong neighborhood. So that would be this right here, okay? And then you have to figure out like what's happening at the fence. And so they have an open circle where the line meets the fence. And the reason why it has an open circle there is that x is simply less than 1. It's not equal to 1. If it was equal to 1, it would be solid. But it's not, so I'm keeping it open. So that first part is done, and I'm ready to graph part 2. So part 2 is made up of the function x minus 1 quantity squared. and it resides in the neighborhood where x is greater than or equal to 1. So they're indicating that that's the neighborhood on the right side of the fence. And so they did graph the entire function, okay? So I'll show you like what that would look like if you graphed the entire function. And then you would want to erase the part that's in the wrong neighborhood. So that would be like everything over here where the green line lives. And then you just simply need to determine what's happening at the fence. And they're saying that this guy has an equal to, because it's greater than or equal to. So he lives on the fence, and that's why there's a solid point there. So this is the graph of our piecewise function. Okay, now the ones that I'm going to have you guys graph, it's going to be all linear pieces, but this was like a nice simple illustration of like the steps that we follow when we're graphing piecewise functions. So let's actually do one from start to finish, okay? So in problem number 2, we have the function f of x is equal to, and one of the pieces is 2x minus 1 on the domain from negative 2 is less than or equal to x is less than 1, and the second piece is negative x plus 3, and that lives on the domain 1 is less than or equal to x is less than or equal to 4. Ooh. All right, so the first thing we do is we need to put in our fences. So I do like to use highlighters for my fences, and I have a few fences here because I have a fence at negative 2, I have another one at 1, and I have another one at 4. So that's where I'm going to put my fences. So I've got this one at negative 2, this one at 1, and this one at 4. Okay. So now I'm just going to simply lock all these things in so I can't move them. So once you have your fences in, you're now ready to graph the pieces. Now I would graph each piece one at a time because you're going to graph the whole thing and then you'll erase the parts that, well, aren't in the proper neighborhood. So I'm going to start with 2x minus 1. Okay, so that means I'm starting at negative 1 on the y-axis. My slope is 2, so I'm going to go up 2 and over 1. Okay, so I'm just going to do that. And then I'm going to draw in my line. So that's the whole line of 2x minus 1. So now what I need to do is I need to erase the parts that are in the wrong neighborhood. So this line exists between negative 2 and positive 1. So anything that goes beyond negative 2 and beyond positive 1, I am erasing. Okay. So now I just need to figure out what's happening at the fence. So at the fence where it meets with negative 2, you see how it says less than or equal to? So that means I'm going to have a solid point on that fence. Regarding the fence at 1, it's simply less than. So that means I'm going to have an open circle. So that's the first piece. Looks pretty good, right? Thanks. Okay, so now I'm ready to graph the next piece, but let me just lock all those in because, well, I'm going to be erasing and I don't want to erase all my hard work, right? So now I'm going to graph the piece negative x plus 3. So to graph that, I'm going to have to start at positive 3 on the y-axis. My slope is negative 1, so I'm just going to go down 1, right 1 repeatedly. And then I can draw in my line. So I'm drawing in the entire line, and then I'll erase everything that's in the wrong neighborhood. So that means I'm erasing everything over here because this piece only lives in between 1 and 4. So I got to erase this part over here. And then it's time for me to think like what's happening at the fences. So according to my inequality, 1 is less than or equal to x. So at the fence of 1, I am going to have a solid point there. And x is also less than or equal to 4, so I'm going to have a solid point there. And there we have it. That's the graph of my piecewise function. Isn't it great? Now for my domain, we've been identifying domain and range from a graph for, well, definitely over a week now, so we should be really good at this. So my function goes as far left as x is equal to negative 2. It's nice and solid there, so I'll use a bracket. And then there's a weirdness at 1, but it's okay because it's solid there. And then it goes as far right as 4, and it has a bracket there as well. For the range, I'm thinking about my y values low to high, and this one goes as low as y is equal to -5, and it's solid there. And then it goes as high as y is equal to 2, and it's solid there as well. So that's my range. Okay. So when we graph piecewise functions, the first thing that we do is we put in our fences. We look at those inequalities. So number 3 has a fence at -1 and a second fence at 2. So only 2 fences here in number 3. One is at -1 and the other one is at 2. Okay. Once I have my fences in there, I am going to be ready to graph some lines. Okay. So my first line is x plus 2. So that means I'm going to start at 2 on the y-axis. My slope is 1, so from there I'm going to go up 1, right 1, repeatedly. And then I can draw in the entire line. Then I need to erase everything that's in the wrong neighborhood. Now this piece lives in the neighborhood where x is less than -1. So anything beyond that needs to be erased. So we're talking about all of this stuff. So now I just need to consider, like, what is happening at the fence? Well, x is less than -1. So that means I'm drawing an open circle where it's on the fence. Perfect. Now I'm all ready to graph the next piece of my line. Okay, 3x. So for me to graph 3x, I need to start at 0 on the y-axis because this is really like 3x plus 0. And from there, I'm doing what the slope says. That means I'm going up 3 and over 1. And then I can draw in my line. Once I have it drawn in, it's time to erase whatever's in the wrong neighborhood. So this piece lives in between -1 and 2. So it lives right in between my 2 fences. So let me erase the part that's not in between. Perfect. And then I just need to think what's happening at the 2 fences. So at the fence at -1, x is less than or equal to. So that means I'm going to have a solid circle. At the fence of 2, x is simply less than 2, so that means I have an open circle there. And now the second piece is all done. So now we're ready to graph the third piece of our function. It has the equation -x plus 1. So that means I'm going to start at +1 on my y-axis. The slope is -1, so from there I'm going to go down 1, right 1. And then I'm going to draw in my entire line. Now this piece lives where all my x's are greater than or equal to 2. So I need to erase any pieces that are in the wrong neighborhood. And then I just need to consider what's happening at the fence. X is greater than or equal to 2, so that indicates a solid circle. So here's my function. Isn't it great? Now I'm ready to identify my domain and range. So this graph goes as far left as -infinity. There's weird stuff going on at x is -1, but solid saves the day and I can move on. It's also a little weird at x is 2, but solid saves the day, so then I can move on. So this thing has a domain of all real numbers. It goes left forever, right forever, and everywhere in between. As far as the range goes, it definitely is going low forever. As I move from low to high, there are some weird spots along the way, but I am solid until I get to 6. 6, I have an open circle, and then it doesn't go beyond that. So my range is from -infinity to 6. So this is how we graph piecewise functions. So let's go backwards. Let's actually write piecewise functions. Okay, so when we write a piecewise function, we have to write a rule for each piece of the function. We also need to identify where that piece is happening. So in number 4, I technically have 3 pieces. One of my pieces is given by the parabola y = x². The next piece is that simple point at y equals 6. And then the third piece is y is equal to 10 minus x. So I'm going to have my function notation equals, and I'm going to have my bracket. And really, they've already identified my 3 rules for me. So the first piece has a rule of x squared, the second piece has a rule of simply 6, and the third piece has a rule of 10 minus x. What I need to do is I need to figure out where these things are happening, okay? So we approach this much like we would approach finding the domain of a graph, okay? We want to think like, what is the domain of each piece? So that first piece, that arrow, is indicating that it's going left forever. So I'm going to actually use interval notation. I feel it's easier for students to do this, and that's okay for us to do this, all right? So it starts left forever, and then it ends right here. So it's ending when x is 2, and because that piece is ending at an open circle, I am going to use a parenthesis. Now, when it comes to that y equals 6, it's a single point. It's happening in one place, and it's happening only at x is equal to 2. So I do need to write this exactly as I said, x equals 2. And then that third piece begins when x is equal to 2. There's an open circle there, so I am going to use a parenthesis. And then it ends right here when x is 6. And because there's that closed circle, I'm going to use a bracket. So this is what my piecewise function looks like. Now, when it comes to domain and range, we're talking about the domain and range of the entire function. So our entire function does go left forever, so negative infinity. There is some weirdness going on at x is equal to 2, but it is solid there, so I don't have to stop. I can keep going, and I will continue until I get to x is 6, where it's solid, and I have a bracket. For my range, my function is going as low as y is 0, and there is a solid point on my graph there. And then remember, this arrow here is indicating that it is going up forever, so that would be to infinity and beyond. So number 4 was actually kind of nice because they gave us all the rules, but like they don't always do that. And so the functions I'm going to have you finding the formulas for, they will be made up of linear pieces. And so we can write lines like this, y equals mx plus b. So m is our slope and b is our y-intercept, okay? So those are the 2 things that you want to think about when you look at each piece of your piecewise function. What is the slope and what is the y-intercept? So this first piece here, I can look and see that my slope, if I'm thinking rise over run, is 1 because I am consistently going up 1, right 1, up 1, right 1. It also has a y-intercept of 1. I can very clearly see that the y-intercept is 1. So for that first piece of my piecewise function, I'm going to write mx plus b. M is 1, so 1x. B is also 1, so plus 1. And then I need to define where this is happening. Well, it starts right here with an x value of -4, and it's solid, so I'm going to use a bracket. And then it ends right here with an x value of 1, and it's solid, so I'm going to use a bracket. So now I'm ready to explore the second piece of my puzzle. Let me just erase some of my markings so I can write all over this again. So looking at that second piece, I can see that it has a slope of -1 because it's consistently going down 1, right 1. But here's the tricky part. What's the y-intercept? So in order to figure out what the y-intercept is, I need to continue my line. So I can use a straight edge and I can continue my line. And what I see is that this piece has a y-intercept of 1. I'm sorry, not of 1, of 0. That's the y-intercept, okay? So the equation for this piece is mx plus b. So -1x and then plus b, so plus 0, and that's totally optional. And then we just need to simply define like where is this piece happening. So let me, make it more visible to us. There we go. So this piece starts when x is 1. There's an open circle there, so I'm going to use a parenthesis. And then that piece ends when x is 3. There's a solid circle there, so I'm going to use a bracket. So here's my function. So for the domain, I'm just doing the domain of the entire function this time. It goes as far left as -4. There's some weirdness when x is 1, but it's solid there, so that's okay. And so it goes as far right as 3, where it's solid, which deserves a bracket. For my range, it's going as low as -3 and as high as 2. So that's how we can write piecewise functions formulas given a graph. Simply look at each piece and be like, what's the slope? What's the y-intercept? You may have to extend the line to see what that y-intercept is, and then simply identify the domain of each piece. And that's how Backer breaks it down.